Ni hao, Wosi Jaume Anguera, and together with my colleague Aurora Andújar from Fractus Antennas in Barcelona, Spain, and David Bai and Milton Wien from Cadence USA, we are going to present the easy design of IoT devices with antenna boosters. First of all, we would like to thank you, the organizers, for letting us to do this presentation in virtual mode. This is the outline we are going to follow. First of all, an introduction. Then we are going to introduce antenna booster technology, and then how this technology is useful to embed antennas in IoT devices. And finally, we are going to draw the conclusions. Well, we are entering the IoT world, so not only people is connected with people, but also things with things. So we need IoT devices to efficiently transmit and receive information. And here is where the antenna plays a very, very important role. The antenna is the key player in this scenario. So here is where virtual antenna takes place. Virtual antenna embeds very tiny antenna boosters, shown in red, in IoT devices. Embedding an antenna booster in IoT device allows to operate at any band, and it's useful for any device. Let's see. For instance, we have several devices with different shapes, different form factors, from a big one to a small one. Do we need to use a different antenna for each device? The answer is no. We can use the same antenna boosters, and the only thing we need to change from one device to the other is to design a matching network, which is faster and easier than to design a customized antenna from scratch. Now imagine that we have this antenna booster for one device, and we want this device to operate at dual band GPS and Bluetooth. And then we need to launch a new product, a new device with different bands. For instance, LTE, low bands of LTE, plus high bands of LTE. Do we need to use a different antenna for each product? No. Again, we can use the same antenna booster for each device, and the only thing we need to change from one device to the other device is the matching network, which is, again, this is easier and faster than to design a different antenna for each product. Where is this virtual antenna technology useful for? Any kind of IoT devices working in this frequency range from 0.5 giga up to 10.6 giga. So everything including LTE, LoRa, Sigfox, ultra-wideband, GPS, Wi-Fi, and for application devices such as trackers, smart meters, smart home and city, and as well as modules and sensors. Here we have a picture to illustrate how small are antenna boosters. We have external bulky monopoles, we have some customized and complex geometries, difficult to adjust, difficult to tune, and in here we have the antenna boosters. You can see how small they are. They are very tiny components, as you can see now in my hand. This has only 5 by 5 by 5 millimeter. So they are one order of magnitude less than the customized antennas. Just to give a reference, the volume is about 100 millimeter cube. So these antenna boosters are really small and very convenient to integrate in IoT devices. So here we have a transition from the past, from the bulky antennas, easy to break, easy to install, and the customized antennas that are difficult to adjust. But here we have the new revolution with antenna boosters, these tiny components you can see in red, and in this case we have very nice examples of two open IoT platforms, plenty of sensors for IoT applications. Let's have a look at this video that summarizes the main features of antenna boosters.
In this super duper smart modern world, connected things are everywhere. Whether you're managing a fleet of trucks, running a smart city, or just checking your fridge, you'll be using antennas to plug into the mystical wireless IoT world.
Last night, you ate 3 pizzas. Shall I order more?
Shh, fridge! Don't be so smart. Anyway, for you guys trying to figure out which antenna is right for you, The whole process can drag and suck up all your patience and money until you find yourself screaming, "Please help me!" But now, your antenna nightmares are over. Introducing the one, the only virtual antenna. This little genius is multiband. It works to any standard or frequency. NB-IoT, LoRa, Sigfox, Wi-Fi, GPS, 3G, 4G, 5G, or whatever G they come up with next, probably 6. And because it's tiny and delightfully versatile, it'll fit in any wireless product, regardless of the form factor and frequency band. Your friendly new little antenna component works just like another chip. Need to reduce your time to market? Use virtual antenna on your project so you can move fast. On to the next one. Or sit back, relax, and
Eat more pizza.
fridge. Oh, go on then.
So in summary, we see that antenna boosters of virtual antenna, they are small components, they can be multiband, they are off the shelf, so ready to use in any IoT device, and they are SMD components. So this is very attractive for mass productions because they can be assembled using a pick and place machine. So let's see the basic steps we need to follow to embed antenna boosters in IoT device. The first step is to place the antenna booster. Usually the corners of the device are the best positions, the best locations, in order to maximize range and battery life. Second step is to design the matching network to operate at the frequency bands we want. And the matching network you can see here is between the antenna booster and the transceiver. And the last step is to verify that everything works in terms of impedance, efficiency. So at the end, if everything goes well, this means that you will have good range and a good battery life for your device. So let's see step number 1. Here we have some real examples of antenna boosters in IoT products. You see that always the feeding line is close to the corner of the ground plane. This is a multi-PCB, so at least one layer is the ground plane. And as you can see here, this is an antenna booster, and the feeding line is close to the corner of the device. In here we have another example. We have an antenna booster, feeding line. The ground plane will be this area shown here. And we have the matching network with several components and another 50 ohm transmission line here that reaches the transceiver. And also we have another example here with the antenna booster, a feeding line, and then matching network that reaches the input-output port of a transceiver that should be allocated in this area. So as a rule of thumb, allocating the booster in the corners of the PCB helps you to maximize the bandwidth and efficiency of the design we are doing. Second step, we need to design a matching network. So why we need a matching network? Well, imagine this is a device with an antenna booster, a clearance area, so no metallic components in this area. Here we'll have the ground plane populated with all the components and all the electronics, the battery, and so on. Here we have for testing a 50 ohm transmission line and some pads, but without any matching network. So if we measure this, what we obtain is something that is not matched. We should expect something in the center, but it's not. But this is not a problem because we have the flexibility to tune this at any frequency band we want. Imagine we want to match only at ISM frequency bands. Can we do it? Yes. We can use a matching network to put this in the center of the Smith chart. Can we match this simultaneously at low bands of LT and high bands? The answer is yes, with a matching network. So we will see how we can do it. Here we have an example. This is an antenna booster in an IoT device. This is an example of a PCB. And in red, we have the antenna booster. It's only λ/30. It's 12 millimeters. So this is pretty small. With a very simple matching network, we can operate at 900 megahertz ISM 900. You can see that the efficiency, this is measuring a quiet chamber, reaches efficiency of 90%. And in this case, we have a very simple matching network. This is only 2 components. So imagine now we want to upgrade and we want to design a new IoT device, but instead of doing ISM frequencies, we need a multiband case. For instance, this will be the case. A multiband operating at this frequency. So do we need to change the design? Do we need to design an antenna from the scratch? No. We can again use the same antenna booster, and the only thing we need is to design a matching network. In this case, it's 1, 2, 3, 4, 5 components to obtain this nice multiband behavior with efficiencies close to 70–80%. As you can see in blue versus frequency, we have the total efficiency measured in a anechoic chamber. And even more challenge, imagine we want to go beyond this frequency range and we want to reach up to 2.69 gigas, so as to cover many LT bands. Again, do we need to change the antenna booster, or do we need to design an antenna from scratch? No. We can again use the same antenna booster shown here, and the only thing again is to design a matching network that we are going to see now, which is fast and easy. You can see now the blue line, we have a nice efficiency in the low frequencies of LTE, as well as nice efficiencies, about 80% in the high frequencies of LTE, now reaching 2.7. So this gives a lot of flexibility, because only changing the matching network, we can operate at any band we want, from single band to multiband. So these unique features of the antenna boosters of virtual antenna technology, combined with the microwave software of Cadence, makes the designs of IoT devices embedding antenna boosters very easy and fast, and in a systematic way, as we are going to see now. This is the systematic way. First of all, we have our device, which is the PCB. Then we need to allocate the antenna booster, as we showed before. Usually the corners of the device are the best positions. Then we define the frequency bands we need to operate, and we specify the target of, for instance, S11. We want an S11 below -6 dB or -7 or even -10 dB in these frequency bands. And that's all. That's all. With that, the software will end up with the topology and the values of a matching network ready to use in our device. So let's see a real example. Imagine we have a device. This will be our device populated with all the electronics, the batteries, the chip, and so on. We have the antenna booster close to the corner of the PCB, of the ground plane. Then we need to attach a 50 ohm coaxial transmission line to test the input impedance without the matching network. So this S11 data is the data that we import to the software, and we can run the simulation. So this, imagine, can be your device. Okay. So with this S11 data, we import to the software, to the microwave office, and we specify the frequency range we want to operate, as well as the target of S11. I want an S11 below -6 dB across this frequency range simultaneously. And that's all. In less than 2 or 3 minutes, the software, if there is a solution, it will find a solution. In this case, it finds several solutions, several matching networks. In this case, 2 matching networks with 6 components where the cost is 0. Cost 0 means that the matching network obtained by the software has an S11 below -6 dB in the frequency range we have specified. Also, it gives another topology with less components, in this case 5, with 5 components, but the cost is not 0. It's close to 0, it's 0.17. This means that perhaps in some frequencies, the S11 is above -6 dB. But this means that this software gives you the flexibility to test several matching networks from 6 components, 5, whatever. The software selects how many components we are going to need. Perhaps only 1 if it's single band, or 2. And in those cases where we are doing a multiband, perhaps we need 4, 5, 6, or even 7. But the software gives everything, the topology and the values we need to take and build directly in our device. So the components we are going to use in the matching network are SMD components. 0201, 0402, 0603. So these components need to be placed in the paths of your layout. And those paths can be easily modeled in the software. So at the end, the matching network, that is the synthesis, takes also into account the path effects, as well as you can select with the software to use available commercial components. In this case, we're using from Murata. So you can see here, this is 1, 2, 3, 4, 5, 6 component of the matching network with the part numbers. So these part numbers are the ones that we are going to take from the simulation, bring to our device, and test in our device. So let's see. In this case, with the S11 data that we imported from our device, we obtain a matching network, and let's see a real example. Here we have it for a smart tracking platform. So we should operate at this wide frequency range simultaneously, from the low bands of LTE to high bands of LTE. So we tested first the S11 without any matching network. We imported to the microwave office, and the microwave office in 2 or 3 minutes end up with a matching network that in this case it's 6 components. You can see here, for instance, the first component it's 0, it's a 0 ohms resistance, go here. The second component, it's a shunt inductor, is this blue component here. The third one is a series capacitor, goes here. The fourth component is shunt inductors, it goes here. The fifth component is a series capacitor, it goes here, and so on. The sixth is a shunt inductor, goes here, and finally this is a series component, which is a capacitor, that goes here. In here we have the 50 ohm. In this case we have a testing 50 ohm coaxial cable, but you can have your module, your transceiver, just connected at this point to feed the antenna system. So ready to transmit and receive information. So at this point here, which is this point here, which is this point here, we have the 50 ohm or close to 50 ohm across this frequency range. And here is how the S11 looks like. The blue one is the one that we obtained from the simulation. It means that we obtained the S11 from the device, we imported to the microwave office, the microwave office end up with a matching network, and the blue one is, well, this is something that you should expect in the lab when you build in your device. So we take the matching network obtained in the simulation, we build in the device, and we obtain the ping line. As you can see, the agreement is very, very good, and it achieved an S11 below -6 dB across the frequency region of interest. And this is a very easy and fast way to do it, and it's very fast because it's less than 1 hour. So from taking the S11 data from your device, bringing to the software, doing the optimization, obtaining the matching network, building this matching network in your device, is less than 1 hour. This is very fast. So in one day, you can test several matching networks and conclude which one is best for your design. Also, we have compared this method, this systematic method in blue, with a matching network obtained by a human being, by an expert in pink color. You can see that both matching networks are pretty much the same. And in this case, only 6 components were needed with this systematic method. So even it's much simpler than the matching network obtained by the human being. And not only that, if we compare in terms of efficiency, the matching network obtained with this systematic, fast and easy method provides an efficiency that it's better than the one obtained by trial and error by a human being with engineering force. You can see the blue one is the artificial intelligence-based matching network. It's much better, and in this case, even much better. So this is a very powerful method to design IoT devices embedding antenna boosters. So perhaps in the future, robots can embed antenna boosters in IoT device. So perhaps we have time to do other sophisticated and fashion things as engineers. So to conclude the presentation, we see that the antenna boosters are small, they can be multiband, they are off the shelf, so ready to use. From the very first day we are designing an IoT device, we have the product ready to use, and they are pick and place, they are SMD components, which is very convenient for mass production because the quality of this assembly process is very, very controlled through the pick and place machines. These unique features of virtual antenna in combination with the microwave office software makes the design of IoT devices fast and easy, and faster and easier than to design antenna from scratch. And here we have some examples of antenna boosters. This is a proven technology through many commercial products worldwide for applications such as trackers, smart meters, smart home and city farm, and modules and sensors. We would like to acknowledge the European Commission and Spanish Ministry, as well as Cadence, for supporting the research done in this presentation. And xie to everybody attending. It's a pity we cannot be with you face to face today. Hopefully next year the situation is much better and we can be with you. It will be a pleasure to be with you. If you need more details on this, please, you can visit this webinar. It's free access for this presentation. So on behalf of Fractus Antennas and Cadence, thank you very much for your attention. And if you have any question, please, you can use my email as well as David's email to further discussion. It will be our pleasure to have discussion. So thank you very much. Xie xie.